So now that we've discussed what the derivative means, that it tells us the slope of a tangent line at that point, or that it tells us the rate of change at an exact point, we're going to develop some formulas that are going to allow us to find the derivative for any function that we face. So in this video, we're going to introduce in total 5 new rules, starting with these 4 here. That the derivative of just a constant, the derivative of just some number, is 0. The derivative of a linear function is its slope, it's whatever m is. The derivative of some constant times a function is that constant times the derivative of the function. And if f of x is some power, x to some power, then f prime of x is n times x raised to the n minus 1. So if I can make a suggestion at this time, I would take a second and I would write down these 4 rules. Because as you move forward, as we look at these different functions, we're going to be applying these 4 rules. Alright, so here we've got a few different functions that we're going to look at. And we're going to use those rules. So for part A, this is y equals 3x minus 8. Well, from our rule about linear functions, then y prime would equal the slope of that line. The slope of this line would be 3, m would be 3, so y prime is just 3. For part B, this is x to some power. So we're going to use that power rule. F prime of x would equal, notice this is x to n, so 13 is in place of n. F prime of x will equal 13x to the 13 minus 1. And just using some simplifying, f prime of x would equal 13x to the 12th. For C, we have 3 times some x to the n. That is a constant times a function. So we're going to say y prime would equal 3 times the derivative of x to the 7th would be 7x to the 7 minus 1. So simplifying that, y prime will equal 21x to the 6th. This fact here is going to help us deal with some fractional looking functions. That you have x to some power in the denominator, that is the same thing as x to the negative a written in the numerator. We're going to do that because that allows us to apply this power rule. So if you look at D, this is f of x equals 1 over x to the 6th. I'm going to first rewrite that as f of x equals x to the negative 6. What that does is it allows me to apply the power rule. So now f prime of x equals, we drop that negative 6 down, this would be negative 6x to the negative 6 minus 1. So f prime of x equals negative 6x to the negative 7. For E, what we should notice is that there's really an invisible 1 on this x. So I can rewrite this function y as y equals 3x to the negative 1. And then now we have a constant times some function. So to do y prime, I would say that equals 3 times, and then when we take the derivative of x to the negative 1, we drop that negative 1 down, x to the negative 1 minus 1. So y prime equals negative 3x to the negative 2. Now, both of these examples would be fine written like this. But we can also rewrite those by moving the negative exponent back to the denominator. In fact, either way is technically correct, but it probably just looks a little bit better if we rewrite both of these. This would be f prime of x equals negative 6 over x to the positive 7th. We make that exponent positive by moving it to the denominator. And so here this would be on this side, y prime equals negative 3 over x squared. The next rule that we want to add is if we have multiple terms throughout some sort of function, then what we do is we just simply take the derivative of each term. So f of x plus or minus g of x, if we want to find the derivative of that, it's f prime of x plus g prime of x, or if there's a minus, we subtract the two. So like for this example, for part A, we want to do the derivative of each term. So the derivative of 5x squared is 5 times 2x to the 2 minus 1 plus, now notice this second part, 7x minus 4, this is technically just a linear function. The derivative of that linear function would be 7. So the derivative here would be y prime equals 10x plus 7. Over here, we've got a little bit of an issue in that we've got this fraction for part B. So I'm going to rewrite this before I take the derivative. I'm going to say this is f of z equals 13z squared plus 5z to the negative 1 over 2. And now we can go through and do each one of these derivatives term by term. F prime of z equals 13 times 2 z to the 2 minus 1 plus, if I drop down that negative 1, 5 times negative 1 z to the negative 1 minus 1 over 2. And just doing some simplifying, this would be f prime of z equals 26z minus 5z to the negative 2 over 2. And as we did before, I can make that z to the negative 2 positive by moving it to the denominator. So I'm going to say this is f prime of z equals 26z minus 5 over 2z squared. Now the whole reason we do these derivative functions, or we rewrite them, is that we recognized previously the derivative changes as you move along some function. And so by finding these derivative functions, we can plug in any value of x and determine what the derivative is at that point. So let g of x equal 2x cubed plus 5x minus 4. And we want to find the derivative at these points. Well, in general, then, g prime of x would equal, using our rules, the first term would be 6x squared. The derivative of the 5x would just be 5, and the minus 4 would go away, right? If we think of this second part as being like a linear equation. Or you can start thinking of the derivative of a constant being 0. But either way, g prime of x would equal 6x squared plus 5. So now if I want to find g prime of 0, I'm just plugging 0 into the derivative function. So 6 times 0 squared plus 5, g prime of 0 would equal 5. If I wanted to find g prime of 2, I'd plug 2 in. G prime of 2 would equal 6 times 2 squared plus 5. And if you work that out, g prime of 2 would be 29. And if we wanted to find g prime of 5, g prime of 5 would equal 6 times 5 squared plus 5. G prime of 5 would equal 155.